Hello everyone, welcome to the module 4 for the Essentials of Turbulence class. So in module 4 we are going to be dealing with the statistical description of turbulent flows. So what do I mean by statistical? We are going to look at averages, variances, even third order moments, fourth order moments and so on. But the most commonly used are means or averages and variances. Now, here, the statistical description, we've discussed this a little bit when we started to discuss turbulence. The reason for using a statistical description is because you have a random variation in flow quantities, isn't it? It is seemingly random. There is a reason for it, and we'll come to that as well. But there is this variation, unsteady variation of quantities. Velocity is varying continuously and it is varying with time. So that might not make a lot of sense to us because it might look chaotic. So in that sense, what can make sense to us is probably, say, the average or the RMS value or the variance. RMS or the RMS squared is the variance. So that is what this chapter is entirely about. This module is entirely about. We are going to be dealing with the statistical description of turbulent flows. So these are the contents. We are going to be dealing with the random nature of turbulence. So we'll discuss that a little bit. And again, keep this in context of how turbulence is actually described. There is a seemingly random behavior. It is not actually random, because if so, we couldn't use the Navier-Stokes equations, right? We'll discuss that as well. And we will try to describe some random variables. We'll try to characterize random variables. All of this is because the fluid behavior is seemingly random to us. So can we characterize them by some random distributions? We'll look at that. So in the context of that, we will discuss cumulative distribution functions, probability distribution functions. We'll look at some statistics. We'll look at some examples of PDFs, joint random variables, joint PDFs. This is because velocity is a vector. Velocity has multiple components, isn't it? It has 3 components, u1, u2, u3. So it is not a scalar. And in that sense, you would have to consider joint random variables as opposed to just a single random variable. Although we'll start discussing a single random variable, then move to joint random variables. So subsequently, we'll have to go to joint PDFs. We'll discuss correlation coefficients, conditional PDFs. We'll have some discussions on random processes. We'll describe random process sample paths. Statistically stationary random process, we'll see what that is. Autocorrelation functions, frequency spectrum, integral timescale, statistically stationary Gaussian process, and so on. So we'll look at some of these things in this module. This is the source. We are using a lot of content from Pope's book. Now, let's start to describe what the random nature of turbulence is. And again, I cannot reiterate this enough. The flow is seemingly random to us. It is not actually random. So what is shown here on the slide is a plot of the velocity variable of an nth repetition of a turbulent flow experiment. So the velocity is measured at a particular point in space and possibly at a particular point in time as well. But each dot in this graph represents a separate repetition of the same experiment. You have velocity on the y-axis and the repetition on the x-axis. Each dot represents the velocity measured at a particular point in space and at a particular point in time for a different repetition of the experiment. As you can see, the velocity seems to be differing. You would think that if we perform the same experiment multiple times, we would get the same value of velocity at that particular point in space and particular point in time. But that is not the case. You have this so-called random variation. Sometimes it is 5, sometimes it is 7, sometimes it is 10, sometimes it is 15. So there's this variation in velocity. And it looks random to us, right? Now, what does randomness mean, isn't it? It means, from a probability standpoint, if you consider an event A such that u is less than 10 meter per second, then again, u is a specified component of velocity at a specific position in time. For an experiment conducted multiple times under the same conditions A, then the event A is neither certain nor impossible, isn't it? That's what randomness means. The event A is neither certain nor impossible. It can happen, it need not happen. And in that sense, it is random. So if you see here, for the same conditions, if you consider the probability of A being less than 10, of U being less than 10, you can see that only sometimes it is less than 10, other times it is above 10. So that's what we mean. If you conduct the same experiment multiple times under the same condition C, then the event A is neither certain nor impossible. So for a random behavior, you would have to define a probability. Am I right? So that's that. But now the inherent question is, and we've asked this question to ourselves multiple times, if it is so-called random, what is the consistency between the randomness of the turbulent flow and the deterministic nature of the Navier-Stokes equations? Because the Navier-Stokes equations is deterministic. If you solve the equations multiple times, just like you conduct the experiment multiple times, repeated multiple times, if you repeat the solution of the Navier-Stokes equations multiple times, you should get the same answer, isn't it? X plus 5 is equal to 3. You should always get x is equal to minus 3. Now, I agree the Navier-Stokes equations is a lot more complicated. Nevertheless, it is still a set of equations that gives you a unique solution at one particular point in space and time. So then the deterministic nature of that combined with the random nature of turbulent flows as we see it, how do they go together? That's the question we are trying to ask. If the Navier-Stokes equations are deterministic, then why are the solutions random? Because this right here should be described by the Navier-Stokes equations, isn't it? It's a fluid flow behavior. Continuum hypothesis is valid. The Navier-Stokes equations apply to these kind of flows. So if you solve for the velocity at a specific point in space and time, you should get this value. And in fact, every time you should get that same value. Then why is it that we are not getting the same value? It has to do with the boundary conditions and the initial conditions that we apply. From a solution of an equation perspective, it has to do with the initial conditions and the boundary conditions and the material properties. From a physical perspective, it has to do with the sensitivity to those conditions. So let me explain this in more detail. Consider the condition C of the experiment. The same conditions. These conditions are incomplete just by the conditions alone, so we have to specify certain boundary conditions, isn't it? So what happens is, if you consider an experiment, everything is not, for example, machined perfectly. If I consider a pipe, the inside surface, there could be some roughness associated with it. You could try and eliminate as much roughness as possible by a precision machining. You could still have some roughness associated with the inside surface of the pipe. And that, I'm afraid, is to an extent uncontrollable. Can we quantify the roughness exactly? Because we intend it to be smooth, but it is not perfectly smooth. So there is some roughness associated with it. Let's say you are doing an experiment on water flow in a pipe. The water need not be perfectly clean. Yes, you want it to be clean, say you want to use distilled water, but it might not be perfectly clean. There might be some impurities in it. Once you have impurities in it, the way it behaves could be different from a perfectly clean water. So the impurities could affect the fluid properties. That could affect the heat transfer, for example. So it's these kind of uncontrollable things in experiment that creates differences when you start to run the experiment multiple times. That roughness could lead to different kinds of behavior. Now one can argue, you can argue that, well, even if the flow was laminar, you would have the same surface roughness, same impurities. Then what is the big deal with turbulent flows? That we get this kind of random behavior. And that has to do with the sensitivity to initial conditions, or sensitivity to, I should say, initial conditions, boundary conditions, and material properties. So the sensitivity to such perturbation, the second point here, is what I want to emphasize. In laminar flow, it is not as sensitive to those perturbations, whereas in turbulent flow, it is. That is the difference between laminar flow and turbulent flow. The viscous diffusion, the viscous effects that exist in laminar flow diffuse any such sensitivity to the perturbations in laminar flow. Whereas in turbulent flow, the viscous effects are less, so the perturbations persist, they propagate, they amplify. And that is the difference between laminar flow and turbulent flow. So in order to illustrate that, Lawrence actually did a time-dependent system experiment. And this was a numerical experiment. He characterized a system by 3 straight state variables. Let's call that x, y, and z. And all these are time-dependent. Now these variables evolve according to the ODEs shown in the slide. So you have x dot equal to sigma times y minus x, y dot equals to rho x minus y minus xz, and z dot is equal to minus beta z plus xy. So clearly a nonlinear system, but an ODE. Gave some values to the constants. Sigma is equal to 10, beta is equal to 8 over 3, and rho is equal to 28. Now, when we solve this equation, we'll have to specify, it's an ODE, it's a time-dependent ODE, system of ODEs to be specific, x, y, z. So we will need initial conditions, and we start with the original initial conditions are this one. X of 0, y of 0, and z of 0 are 0.1, 0.1, and 0.1. Simple. This is actually a simple system. It's non-linear, but it's still an ODE that can be solved. Now, let me just skip a couple of slides to show you what the solution is. I'm only plotting x here, and x looks like this, the solution. Clearly, some kind of chaotic behavior is there. It doesn't look periodic, although it may seem like, but it is not periodic. And it seems to be fluctuating quite a bit. There is an irregular behavior, correct? Now, if I take that same system and try to perturb the initial conditions. Now, my new initial conditions are 0.100001, and then y and z I keep it the same, so 0.1 and 0.1. Let us see what happens. With that initial condition, so I just varied it by just a little bit, by almost 5 orders of magnitude, isn't it? Varied it by 5 orders of magnitude. And then what happens? And I solve the same system. Let's see what happens. So this is the old one and this is the new one. So if you see here, everything seems pretty similar here, here, and then suddenly I start to have a difference somewhere here. Isn't it? In this window, I start to have some difference. So initially, although the old and the new are staying the same, there starts to be some difference in that region. So that's what we mean. So if you see here, they are initially indistinguishable, but by t is equal to 35, they are quite different. By t is equal to 35, they start to be quite different. So just by varying almost 5 orders of magnitude, the initial condition, and of only one variable, which is obviously dependent on the others as well, you start to see this variation. A significant variation. How can we quantify that variation? Let's just subtract these two signals. Subtract these two signals, and obviously it is 0 initially, and then you start to see minor changes, and then it starts to just fluctuate wildly. So there's a big difference when you look at this region. So a minor change in initial condition, although initially it was staying the same, it did not bring about a significant change. After some time, it started to really fluctuate wildly. It started to show those differences. And that's what I'm talking about. It is this sensitivity to initial conditions that turbulent flows exhibit. It is this sensitivity to initial conditions that turbulent flows exhibit that you wouldn't see in laminar flow. What happens in a laminar flow is, with this change in initial condition, these fluctuations will die out immediately. How do they die out? What is the physical mechanism that causes it? It is the viscous diffusion. These perturbations won't persist. They won't amplify because the viscous diffusion actually dampens all those perturbations out. In turbulent flows, the viscous effects do not dominate. They are negligible. Inertial effects are more dominating. So there is no mechanism to actually diffuse these perturbations. So these perturbations persist and in a lot of cases amplify, and that is what you're seeing. From here on, it actually amplified as we went forward, and then it sort of went out of control. And this is in fact for a much simpler system than the Navier-Stokes equations, isn't it? A much simpler system. You have an ODE, whereas you have a system of ODEs, whereas in the Navier-Stokes equations it's a system of PDEs, partial differential equation. You have second derivatives, you have nonlinear terms. Here also it is nonlinear, but you have nonlinear derivative terms. You have multiple components. It's a vector. You have the pressure gradient. You have additional set of equations that governs pressure. So it's a lot more complicated than this relatively simpler system that Lorentz developed. But however, it illustrated the fact that if such a simple system could exhibit that sensitivity to initial conditions, then just imagine how sensitive the Navier-Stokes equations would be to the initial conditions. And that is the second point. We already discussed this quite a bit in modules 1 and 2. But the fact that there could be some variations in boundary conditions, in initial conditions, in material properties. I'm talking with respect to an experiment. There could be some perturbations in these conditions, and how the turbulent flow responds to it is the key here, right? How it responds to it. That sensitivity to initial conditions is what makes turbulent flow very different from laminar flow. That is where it is different. Now, that is from an experiment perspective. From a simulation perspective, let's say you're simulating, you're solving the Navier-Stokes equations. How is the boundary condition different? You can, if you say x is equal to 0 here, x is equal to 1 here, always it is going to be x is equal to 0, x is equal to 1. So there, a precision error comes into play. The precision that you use for your computer comes into play. There could be some minor variations in the value that you give. Are you giving 0.0000 or are you giving 0.0? That matters. So that precision could lead to some variation. That precision in all the values that you specify could lead to some minor variation, and that could propagate. So even then you will have some variation. But in an experiment, for sure, there are a lot of uncontrollable things which can lead to perturbations. And that sensitivity to perturbations is what differentiates turbulent flow from laminar flow. So that is what is prescribed here. Now, obviously, you saw that there was there were a set of constants here, right? Sigma, beta, and rho. Now, you would think that the values of these, the way the system behaves, would depend on the constants. Of course, in the Navier-Stokes equations, it would depend on what the density is, what the viscosity is, absolutely. So in the same way, the system would behave differently for different values of sigma, rho, and beta. So that's what we are trying to say here. The qualitative behavior of the system depends on the coefficients. For instance, below a critical value of rho star is equal to approximately equal to 25, the system goes to a stable fixed points. That is, the state variables tend asymptotically. So at that point, the values of x, y, and z, they just tend to be zero asymptotically. They don't start to fluctuate like this. Even if they don't tend to zero, they tend to a certain constant value asymptotically. Whereas if it is above 25, they start to vary wildly. So that is what we mean by this. However, for large values, a chaotic behavior ensues. So it also depends on these coefficients, isn't it? And that coefficients determines how the system behaves. So that's what we were trying to show with this simple system here. So that takes us to the characterization of random variables. So now that we know that our fluid variables, variables like fluid behavior varies or behaves in a random manner, it would be wise to start to characterize random variables. Okay, so if you take the Navier-Stokes equations and for laminar flow, you can calculate U exactly and the answer will be accurate. However, for turbulent flow, since U behaves like a random variable, it is inherently unpredictable, isn't it? Because your boundary conditions and initial conditions lead to some sort of variation. The system responds to such variations by being very sensitive. So it exhibits a randomness. In that sense, we cannot predict it. We cannot predict the velocity. So for turbulent flows, since U is behaving in a random fashion, the value is unpredictable. So does that mean the theory of the Navier-Stokes equations is wrong? No, that is not the case. It just means that you can use that theory to predict the probability. So now that takes us, we should start to see whether we can predict the probability of the event rather than predict the value exactly, because it behaves in a very random manner. So why don't we start to predict the probability of a certain event happening? That is what we are going to be focusing on next. So we will start to do a characterization of random variables. We'll look at what probability means, and that will take us to the cumulative distribution function, which will tell us what the probability of an event is. Then we will look at the PDF, which is the derivative of the probability as well, derivative of the cumulative distribution function. So what we have done here in this particular class, as an introduction, we've looked at the random nature of turbulence. And again, I couldn't emphasize this enough. It's a seemingly random behavior. The moment you're using the Navier-Stokes equations, you cannot say that the velocity is random. It is seemingly random because the deterministic and randomness don't go together. You either say that you're not going to describe turbulent flow behavior with Navier-Stokes equations because they are random, or you say that you are going to represent the turbulent flow behavior with a deterministic set of equations like the Navier-Stokes equations and do not call them random, though they are seemingly random. And that is what we have touched upon in this class. In the next class, what we'll do is we'll go into more detail about characterizing these random variables and look at examples of CDFs and PDFs. Thank you.